All right. So thank you all for coming tonight to talk about the mother of all demos and rediscovering the birth of modern interactive computing. At least that's the title. Tonight we have Howard Bussey, correct?
Yes.
Perfect.
Perfect.
Let's see. Howard's first computer job, he found and fixed garbage collector bug in Snobol implementation on a time-sharing computer. I can safely say I've never worked with Snobol.
No,
What was that?
you are missing out.
Yeah.
Absolutely.
Software at Bell Labs for the 5ESS. Also going to have to ask what that is. He contributed to the research that was standardized as asynchronous transfer mode, although they standardized cell size would be 1 or 2 kilobytes. At Kodak, he worked on several online services. At RIT, he worked on EPLS and modeled some vehicle systems. Currently tutors dyslexic students, does recreational programming, that sounds funny, and volunteers with the Rochester IEEE, which is where I think he and Kristen know each other, or Christine know each other. So Howard, off to you.
Okay, thank you. Hey, 25 years ago, I gave a talk in a hall in Berlin where the soundboard was probably 2 square meters. And that didn't bother me, but I'm a little nervous tonight. It's been a long time. So I hope you all will bear with me if things don't go completely as well as I hope they do. In 1968, I was a high school junior when this demo was given. So I have absolutely no connection to it other than that time-sharing system was the same computer, an SDS 940, that the mother of all demo, that was the hardware base for the mother of all demos. And it's the same software system also. That was the same operating system and all that, plus a whole bunch of custom software that was written as part of the work behind the mother of all demos. Now, the mother of all demos is a name given, no, posthumously is not correct, but well after the fact. And the system that Doug Engelbart created he called it NLS, N like Nancy. And that was because one of its predecessors was called the offline system. And it allowed you to batch up processing and launch it with a paper tape. Since that was the offline system, OLS was taken. So when they had the online system, it was called NLS. So let me talk a little bit about some of the things that led to NLS. First, oh, I didn't share my screen, did I? No, sorry about that. So I'm going to talk about some of the predecessors. Some of the predecessors, well, you've probably all heard of Vannevar Bush and the Memex. This was supposed to be a system that allowed you to carry around all the information you needed with you. And I suspect that would be very difficult given the 1940s kind of time frame for Memex. Vannevar Bush had a lot of jobs. He was a professor, and one of his students was Claude Shannon, who is the father of information theory, and he did a lot of work at Bell Labs. Some other predecessors or inspiration was, this should be Stuart Brand, not Stewart Brand, I'm sorry. And it is indeed Stuart Brand of the Merry Pranksters, Reed Casey for that, and also the Whole Earth catalog. And I copied this about Stuart Brand from Wikipedia. He assisted Doug Engelbart in creating this mother of all demos. It shows hypertext. It shows messages, mouse. It's given to the Fall Joint Computer Conference in 1968. And both Brand and Doug Engelbart thought that the computers would be used to kind of reshape the world. I'm not sure that's worked out, but we'll talk about that kind of thing later. There's some interesting, so those are predecessors. There's some foundations. The main foundation is the SDS 940 computer. Scientific Data Systems is the company. This computer had a 1.75 microsecond cycle time, and to store a register into memory, that took 2 cycles. To load a register, that took 3 cycles. I never quite understood why loading was more time consuming than storing. But, you know, and especially most data gets read a lot more than it's written.
Demonstrations that led to modern computing.
So anyway, let's see. It was not a fast computer. You know, it could, I think all the instructions were at least two cycles. Maybe there were some that were 1, but that makes it far less than 1 MIPS. It had accumulator extension, and an index register. That was pretty standard for 1960s computers. It had registers for memory mapping, and it had, well, actually, the 930 did not have memory mapping registers. The 930 had maximum of 4 memory banks of 16 kilowords, and those were 24 bits per word. The system used a modified ASCII where the space character had a character code of 0. So 0 was space, 1 was, well, I've got it wrong. Well, anyway, you subtracted 40 octal from ASCII to get to the thing used. So yeah, I think a space was 0 and all. So Project Genie is another foundation. Project Genie was sponsored by the Advanced Research Project Agency, part of Department of Defense, and UC Berkeley was the contractor. That created the 940 hardware. They added this user monitor mode. They added the user monitor memory mapping, and that let you have 8 pages of 2048 words each, so 2K. So the whole memory space was 16 kilowords or 48 kilobytes. There were these weird things called programmed operations, and that was how you got to the operating system from a user program. But the programmed operations, you set a few bits and you had 64 programmed operations that you could put into your address space, and when one was executed, the system, the computer branched off to whatever routine was designated to run that programmed operation. If you set a couple bits for the programmed operation, that moved your program into the monitor or operating system mode. From what I understand, the 940 hardware and software is the first computer, the first timesharing computer that allowed the users to program in assembly language. And that was pretty cool. The competing thing was a GE timesharing computer, and basically you could just run BASIC. The 940 had QED, Quick Editor, and that was the predecessor for the Unix ed command. It had a debugger, DDT. That was also the link editor, and you could load up the memory mapping registers that you wanted so that you could map in the operating system. And then you could, for instance, try to clear stuck processes. The operating system was kind of buggy, and sometimes it would lose an interrupt, and so the system would wait to process all the characters that the user had typed in. So if you remembered the right incantation, you could clear users who were stuck and other things. Now,
There's a question from chat, real quick.
oh, yeah.
So prior to this assembly, it was punch cards. Is that right?
The previous generation of things would be either punch cards or paper tape. At this time, there were the GE timesharing computers, which used modems, teletype terminals, which would be 10 characters a second. Is that good enough for the question, for the answer? Or, chime in. Yes, so when this demo was given, my father was a physicist at the National Bureau of Standards in Boulder. I helped him write Fortran programs that computed dielectric constant kind of, they computed the dielectric constant for materials such as Coors porcelain or DuPont Teflon. In the 70s, he worked with dust that came back from one of the moon missions and measured the properties of that. And most of the work then was numerical stuff. But let's see, I mentioned this computer also had the Snobol system. So there was a document preparation system that had been implemented on the computer that I worked with in Boulder. So let's see, another thing, scientific data systems, I already talked about that company developing the 930. The way the 940 was manufactured was they built a 930, shipped it off to the custom product division, which updated some of the circuits, and then they shipped it to the customer. Later on, by the way, scientific data systems ceased to exist because it was bought out by Xerox and it became Xerox Data Systems. But Xerox had its own competing line of computers, the Sigma series. So the SDS 940 eventually died a sad death. Anyway, let's keep going. This is where this didn't work. Sorry, I have to reshare because I wrote down to remember to share the computer sound and I forgot to do that. So let's restart, and I have my cheat sheet. So my system introduction is at about 1 minute and 40 seconds in, and that's about as close as I'll be able to get. You can see the video. This is a black and white video.
I hope you'll go along with this rather unusual setting and the fact that I remain seated when I get introduced, and the fact that I'm going to come to you mostly through this medium here for the rest of the show.
Oh dear. So that was Doug Engelbart talking. I'm sorry.
Seated when I get introduced.
Can you turn it down just a little bit?
I'm going to come to you mostly through this medium here for the rest of the show. And I should tell you that I'm backed up by quite a staff of people.
Is that okay now?
Yeah, it sounds about right with your voice. That's perfect.
Okay.
Between here and Menlo Park, where Stanford Research is located, some 30 miles south of here. And if every one of us does our job well, it'll all go very interesting, I think. The research program that I'm going to describe to you is quickly characterizable by saying, if in your office, you as an intellectual worker were supplied with a computer display backed up by a computer that was alive for you all day and was instantly responsive, instantly responsive to every action you had, how much value could you derive from that? Well, this basically characterizes what we've been pursuing for many years in what we call the Augmented Human Intellect Research Center at Stanford Research Institute. Now, the whole session is going to be devoted to trying to describe and present to you the nature of this program. But unfortunately, or fortunately, the products of this program, the technology of it, lends itself well to an interesting way to portray it for you. So we're going to try our best to show you rather than tell you about this program.
So just in the context of 1968, this is a really amazing demo because the video is, I mean, first, it's not a teletype running 10 characters a second. And second, the video for this has been piped all the way from Stanford Research Institute in Palo Alto. They're on Ravenswood Avenue, up to, was it Cow Palace? I forget. I once think I knew where the Fall Joint Computer Conference was, but anyway, up to the Convention Center in San Francisco. Let's see now. I'll skip ahead to my approximate location, and this is a really quick demo of some of the capabilities.
I have a statement with some entities' words, and I can do some operations on these. I can copy a word. I can say that word like copy after itself. In fact, that pair of words I'd like to copy after itself, and I can just do this a few times and get a bit of material there. And there are other entities like text. Say after there, I'd like to copy from that entity point to that point, and it'll copy it. Great. So I could get myself some material on my blank piece of paper, and then I'd say, well, this is going to be more important than it looks. So I'd like to set up a file. So I tell the machine, all right, output to a file. And it says, well, I need a name. I'll give it a name. I'll say it's sample.
Now, in the context of 1968, having files was amazing because, you know, kind of the state of the art then was you had tape drives that you could write to. And then right where I stopped here, I'd like to talk a little bit about the hardware you see. This is a custom keyboard, well, Keyboard Plus. So Doug is using the keyboard. Here on the right is the mouse. And I think it was invented at Stanford Research Institute. And then on the left here is what I call a chord board. This is a chord keyboard. So your fingers, well, if you're Doug Engelbart, your fingers learned to press the rightmost tab of those 5, and that's an A. And a B is the one right next to the rightmost, and a C is both of those together, and a D is the middle one, etc. So if you're good at counting in binary on your fingers, you know, and you're good at translating numbers into between numbers and letters, then you can use that chord board really effectively. I know I taught all of our kids how to count in binary on their hands, and they really loved it when they could say, "No, Daddy, that's a 4." Anyway, a lot of the interactions that you sort of see going on are Doug using that chord board on the left. He doesn't type that much. And then you've seen the spot moving around on the screen. That is the
sample file.
Mouse, or that's the cursor.
And I'll say, please output it. It says it did. And then it comes back automatically with an origin statement or header telling me the name of the file and the date and the time.
So, okay, that's probably the beginning of some, you know, some uninteresting, well, a very general introduction, because this was so such breakthrough that I think he had to get people to introduce to the basic thing. I'm going to scoot off to where he gives a shopping list demo.
Just after my wife called me and said, on the way home, would you do a little shopping for me? So as soon as she said that, I got my system organized. And made a shopping list. So it's got quite a few items on it, and if I want to, I can see that, yes, those are numbered statements. And I can say there are ways I can scan down it, like I can point to 10 and say put it at the top, and I scan up and point to 23, and I got quite a few. And I remember.
So that's how he pages through his text when it's too much text to screen on or to fit on the screen.
That's about as far as it got when she said, well, call me back when you're ready to go shopping and I'll tell you the rest of the things. So let me jump back to the head of the list, and I can do things like begin to reorganize it a little bit. Well, I say after bananas, it's more likely that I'll take the carrots there, and so carrots move right up behind bananas, and aspirin doesn't really belong there. I think aspirin goes after paper towels in the order. Well, pretty soon I would begin to have a lot of trouble keeping that straight. So let me organize it by saying just generally produce. What the hell happened to it?
So for 1968 presenter to say, what the hell happened? I think that must have been shocking. But this demo didn't go perfectly.
All right, I'm going to try it again. I enter a statement that says, hey, that's what I got. Right there? I suspect that something's going wrong, and I would call up the programmer or the hardware man and tell him, I made it. Produce. I really haven't warmed up to this thing yet. So I'll say, well, produce, I'll categorize things. Let me look at it that way, and I'll say, let me move a statement for produce carrots, and I'd like to subcategorize it. So it moved. And there it is. That's what happened.
So he put.
All right, produce, I've got carrots, and I'll move under there also bananas. And in fact, I could move a whole group under there, saying oranges and apples also. So I can begin categorizing things like that, and if I looked at the numbers now, I'd find that these items fit under there as a subset, and I realize I can categorize quite extensively. I could introduce a new thing under there that was something I just invented, a skinless banana, but I have to go there and look at it. So part of our view control, besides this thing we've shown you of showing numbers or not, is also whether we can show you some of these different levels.
So this reminds me a lot of the customized views that have shown up in current software, IDEs where you can collapse function or procedure definitions, or let's see, I think I remember using something like this in spreadsheet. Maybe it was Excel, or maybe it was when I had to use Lotus Notes. But there's quite a bit of work on this customization. And, you know, I think you can probably hear and see the clicking. Well, you can't see, you can hear the clicking, and that's what he used to tell what command it was to be executed. And man, this reminds me of VI, where, you know, everything you do is some command or other. Let's see now. I don't think there's a lot more. You know, there's a lot. Oh no, we need to go to where we can see. You know, he's got a lot of different views. That's just more of the same. But eventually, he starts showing. Let me scoot this back so.
And see or return.
So to start showing the graphical.
But there's another thing I can do.
capabilities,
There's a
again,
root dice that I have here.
an interactive graphical system.
So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, and oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Mark it? Oh, I've already seen that. Produce no. Gee, that's too much. Anyway, so we have this feature of structuring our material hierarchically, being able to move around it very well. When we get a hierarchy, such as I can show you here now, I can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. They do it and all gets renumbered. So I have ways of studying over, making different views, going to specified points, and modifying the structure. At the same time, I've seen that I have a repertoire of different entities, like character, knock off that character, replace a character, make that P. So I have entities of all sorts that I can say I want to do.
All right, so this is a lot more of the same, and I don't see this kind of stuff so much as basic as customized operations in current systems, but still, all of these operations you can do in all the current kind of systems. Now,
So Howard,
yeah.
next time could you turn the sound down a little bit? We can't hear you talk over the video.
I'm sorry.
Thank you.
I can turn it down a little more. Next time I'll pause, perhaps.
Okay, that works.
Okay.
It'll make the transcription easier too.
Oh, it's going to be transcribed and
I might.
put on the cover of the Rolling Stone. All right. Now, Christine put together a poll that I forgot to launch. So we're going to launch this. It shouldn't take very long to get some responses in here. And okay, yeah, I'll talk about the software. I will blow off the, looks like I will blow off the hardware kind of stuff and leave this up for another 30 seconds or something, 20 seconds. And are there any questions or any advice for what to skip and what to go into in detail? All right, the poll says 56, 57, so I'll stop it at a minute. Thank you, everybody. And definitely the software wins. I will say one really quick comment about the hardware. They had a vector generator, a character and vector generator that drew to an oscilloscope screen, basically. And then they had a TV camera pointed at the oscilloscope screen, and that TV camera generated the video that got run on a coax to the offices, or on a coax up to the convention center in San Francisco from Palo Alto. They played some games so that they had it look pretty pretty good from a refresh rate point of view without bogging down the processor or bogging down the memory. The graphics, all the graphics was stored in the 940s memory and refreshed, I think, 15 times a second. So, all right. Well, let's keep going. I'm going to go to, let's see, reshare the screen.
With audio? Oh, yes.
I think I have audio. It was left checked, and I am heading to about 45. Yeah, about 45 seconds.
On those CRTs, the camera, the one that's generating this as well as the one we looked at it with a few minutes ago, have short-term storage in there. It's quite different from long persistence, but gives us the flicker-free display here, for quite a flickery display there. This lets us use that display generation hardware for 3 to 4 times as many display stations as otherwise. You'll notice if we get just the text alone that there's a small effect by that bug smearing, but it's not that bad. And that comes from the memory in the Vidicon tube. Okay, so much for that. I'd like now to have us bring in Jeff Rulifson from Menlo Park, and we'll switch to his console. He's sitting at one just like this, been working independently. Hi, Jeff. Oh. We're not hearing you very well.
Oh, you're not hearing me? How about now?
That's fine.
Okay, so that's the origin of the Verizon "Can you hear me now" advertisement, I guess, or Zoom stuff. Sorry, I didn't write down the time coordinates of when the software started, so there was a few minutes of the tail end of the hardware.
Fine. Okay. All right. I'm sorry you can't see everybody here, but I can't very well either because of the lights. So we're about even.
Okay.
I'd like you to talk to them about the way the special languages have helped in making flexible design available for us of the user features, the functions and the repertoire of the commands, as well as the control dialog for them. And then also, it'd be an interesting example here because you programmers are the ones who most intensely found use for working online as we're building up. Show them how you structured your system guide. Okay?
Okay. I think we can do that. We can get sort of a good feeling for the way the whole system is put together by looking through the system guide. The file is one that system programmers sort of put together, help them get around. NLS right now is getting to be a fairly large program. It's not huge by a lot of standards, but it's getting pretty big. This picture in our system guide file is a picture of the overlay structure. Our overlays are page sizes, so they're not too big in the 940, but each label in this picture names a code file, and each one is 3 to 20 pages long. I mean, 20 text pages if you printed them out. Just to sort of show how you can use a file like this to move around in the code, and also how the code is put together. As I said, each label in the picture is the name of an overlay, which is also the name of that file, but it also...
Now, he talked about the pages, the 2048 word pages, just for a sense of what you can do in that. I ended up rewriting the Snobol pattern matcher. I added a few of the patterns from Snobol 4, and that pretty much, that pattern matcher used up pretty much a whole page of code. So it was, 2,000 instructions or so. And then I think there was another page that was the other part of the runtime. necessary for Snobol, things like, well, the other operations that Snobol had. And you see there's this overlay structure. We didn't talk about the hardware, but the 940 had a fixed head disk or a drum, I'm not sure which one, that had a high speed, IO channel. So reading in some code from the drum to when they changed overlays was a pretty quick operation, and that sort of thing was well done on the 940 because it worked pretty fast compared to compared to say tape operations.
Also happens to be the name of a statement in this file. By selecting one of these pictures and moving there, oh, I was going to do something for you to let you see better. What did I do?
Yeah,
We go back to the origin, start over
brings
again.
back all the parameters.
There. Now let me move up. From the picture, I can move to a little section in this file, which is an area that system programmers leave around notes for each other. It's nothing much interesting here. A little bit about the documentation and the patch space that's left. Right from this spot, I can actually move out to the file. Suppose that I were going out in that control meta language Doug was talking about and just try to see, for example, the routines used in the delete word or move word. Let's go look at move word construct. I just select this link, and here is the file. This file is written in one of these many special languages that we've designed. So I just move down through it, find the move commands. Move, let's look here for move word.
You want to point out how you know it's move word?
Yeah, well, I was just going to look at that, Doug. As I was stepping down through that, I was sort of not only moving through the file, but the structure of the code is rigged in such a way that it's a description of a finite state machine. And so I was following the characters a person would type to execute that command. Down here underneath it, I see that the routine is QMW over in the overlay text edit. So let's go back to that other file. Move back to our picture again and find where overlay text edit is. It's right down here, so we'll go and sort of move down through that one. The text edit overlay illustrates a lot of the different kinds of things that we've done. This file has two major kinds of code in it. First one is many of these different special languages that we've built up. See, I'm trying to find QMW. That's right. It's down here someplace. There we go. Let's see. Oh yeah, it's the two kinds of code. This is still the kind from the other file, but the QMW routine, the first subroutine, the second subroutine that it calls, which is sort of interesting, is move word, or word delimiter, I'm sorry. This routine is written in our content analysis language, and it takes a text string and finds the definition of a word. It looks out for punctuation, and it finds any special blanks around it, and finds pointers that describe that word.
So here, things that are a few characters with regular expressions end up with, as you saw, the half dozen or dozen lines of code and all. The NLS people created quite a few custom or domain-specific languages to do their work, and I was amazed when I saw this. But you know, if you build the simulator for the machine, you know, the abstract machine that is ideal for executing whatever job you have, you can make a really tight, you can make some or write some pretty tight code. And they kept doing that over and over and over again in this system. I'll go a little bit more.
Another interesting one is the next subroutine here. If we look at it, it's in another special language that we've built up. It takes the pointers left over from the delimiter routine and the text in the file and reconstructs the statement after the edit's been done. Let's see. Where was I in this file? The other portion of the file is written in the language that we call MOL. It stands for Machine-Oriented Language. The MOL is in a sense, it's a high-level language in that it has phrase structure and good control.
So he just said this machine-oriented language has phrase structure. That's something I saw when I worked on the 940 software. There were a lot of pieces of code where the original source code was written as like paragraphs, and then there would be a comment for the whole paragraph. The system used a semicolon for an end of line, so if there was a comment, you know, semicolon asterisk was a comment, or you could do semicolon and then, you know, a label. And it was amazingly readable code for assembly language. This MOL that is shown on the screen is a step above assembly language, but as I looked at this code and kind of squinted a little bit, I thought I could recognize a few of the instructions and register references and stuff like that. That is
Constructs like if statements and while statements, but it's also very, very close to machine language, 940 machine language. People talk about the actual registers of the machine, and you talk about doing indirect addressing.
Yeah, no, I don't know if there was much contact between Project Genie and Berkeley, Project Genie at Berkeley, and the NLS work at Stanford Research Institute. But you know, you heard this high level or semi-high, you know, well, anyway, this not assembly language that had while statements or if statements, and those were fairly close, he said, to the hardware. So that kind of reminds me of the people who said C was basically a high-level assembly language for the PDP-11 computers. That might be overstating the case of, or understating the case, but you know, with 1968, it was pretty rare to see a system programming language like this that used the if and while high-level constructs and generated, you know, for the system's programming, you know, that was essentially assembly.
This language has helped us write the kind of fast, tight code that we want, that we have to have to operate in the time-sharing system. And at the same time, it's given us a lot of flexibility. It's also the phrase structure of the MOL is designed to sort of mesh with the block structure of NLS. So here I've got a while statement. To see what's in that while statement, I can move down and see it's three statements, which is an if statement. The if statement is a single if statement, which has an if and an else part. And that whole block opens up to all of that. So by using the MOL like this, I'm able to move around very quickly in my MOL files. Also,
and I have to say, I think that response time is pretty good for a time-sharing system with the cycle times, you know, the fraction of a MIPS kind of execution in there. I think I'm going to scoot on to a few minutes later where Doug Engelbart starts showing the documentation for the system. That was fairly novel, and it was really impressive to see how the documentation was integrated with that hierarchical structured document system that you could see with a shopping list or with the code that was just demonstrated.
I think that the way we've got our records for our programming organized, and then the special languages, using the hierarchy, using the names of places in there as labels of statements, so both NLS treats them as a name it can jump to, the compiler that compiles those files we were looking at treats those as the labels for those subroutines and procedures. It all makes a very nice way to study and integrate, and it's very powerful, exciting sort of thing to show. I hope people do come up to our open house and look at that.
So you just heard Doug talking about the labels. The labels were 3-character labels, so you had to learn what you had to memorize them. They were not words, and the reason they were 3 characters was the SDS 940 word structure stored 3 characters in every word. So I'm guessing that they put their labels or their aliases at 3 characters so that they could just do a search, word by word search through a list in order to find what a alias or reference like that abbreviation would mean.
Let me go down here and open up under usage and say first some application examples. User documentation is a straightforward sort of use. If you were a user here and came and sat down early, you'd want to get familiar with this file. Let's go look. Dave Kasris has written a user's guide. So down the hall in Dave Kasris's office, in his drawer, pulling out the file, we go, and there you see it. The top view of it with the sort of the outline. But I'm interested in just showing this view very quickly. You want to find out the definitions of a lot of terms. Here's sort of a glossary. Well, let's do the thing called freeze a statement, and then open and say, put that at the top. And lo and behold, that statement now is going to be frozen in our display scanning windows from the dotted line down. And then we know about names and jumping to name.
So let's see now. When I saw this, I thought, gee, when did I first see the split screen editor anywhere? And that might have been when I was working on working at Bell Labs in the early 80s, with Unix System 7 on PDP-11s. So this is a good, a good 10 or 12 years ahead of that, where you have a split screen where this is not going to change, but you click up here in order to change the content down below.
And so we can say, what's a bug? Oh, down here tells you what a bug is.
Oh, by the way, the bug is the name for the alias for the cursor.
I see. Well, let's see. What's a level? Select level. Tells you what level is. What's a mouse? That's fun to look at. There's a mouse. You can just point. So you can sit here and point to successive terms, and it goes there. The scanning window goes there. The frozen glossary stays, and you can see the definitions. Very nice. And some of the definitions you can recognize terms here. That's an odd one. Maybe that's a name. Let's just see. Oh, sure enough. It's a sketch showing the mouse and the mouse buttons. Very nice to have documentation like this, and you as a user could sit down and early find your way around in this to find the definitions, descriptions, procedures for commands, like that. So let me go back to my guide.
I was sad that he didn't talk about what the different mouse buttons did, and oh yes, hypertext 1968. Thank you for that comment. Chat.
and say, the next thing, you want to study or modify papers. All right, it happens to be that we wrote a paper for these proceedings. It's in the files. There it is, top level. Gee, it's interesting to study something like that. What does it have to say about user systems? Go to there, open up a level. I only want to see that branch. Oh, what about file studying? Open that up. Oh, specifications of form of view. What about that? Let's just open it all. Now I can read it. Gee, that's an interesting way to study. This material, incidentally, was organized for printing and printed out. And it's from this file directly we printed it out on the form we sent to the printers. And these things up in here, these 3 letters and equals, are special directives we embed in our text, so when the output processor does it, it puts in things like headers. Like this says, make the header on every page be D.C. Engelbart abstract. That's prescribed form. The number between lines, double space it. All these others have characteristics. You get right justification, page numbers, all kinds of control in there. All right, so much for...
All right, so you saw the 3-letter abbreviations again, so that the software can just do a word-by-word search and doesn't have to go on. I see a question in the chat on the files. The files were stored on a disk. I didn't talk about the hardware. They had a 96 megabyte disk called Bryant. I'm not familiar with that. The 940 that I used had a 32 megabyte disk. It had 32 platters. And it had a head. It had a head on a linear motor that was separate for every single platter. The thing was the size of a small SUV. No, it was smaller than a small SUV. How about one of the smart cars, but about 5.5 or 6 feet tall? And let's see, I'm guessing the disc platters were, the disc platters were between 3 and 4 feet in diameter. One day after a disk crash, I walked into the machine room and our computer engineer was standing inside the 940's disk drive. He was standing on the spindle that was strong enough to hold him, because it had to hold, these 32 platters that were all extremely heavy. So let's see, this is that. The documentation details itself are kind of not that important. We've been going almost an hour, so I'm going to scoot ahead to where Doug Engelbart. Oh no, I missed this. Here we're going to see some what amounts to computer-supported cooperative work, where we have, Zoom for exactly
Blackboard, like saying, here, you control it. But let's stay this mode now and add another feature that hardware-wise is available to the kind of display we have. I'd like to see you while I'm working on it. So before I can do that, I'd have to set up my display in a certain way. Set it up so I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it, and I can see your face, and we can talk. So let's do some collaborating. You're silent. Oh.
What do you want me to say?
Yeah. There's nobody here but a large audience, Bill.
All right.
All right. So let's go talk about information retrieval. And there are a lot of things I've been showing them and jumping around and finding your way, relating back to the portrayal I gave about NLS as an instrument on complex data structures. It shows them how we can get around and find things. I showed them the content analyzers to help locate things locally. You had a file kind of classifying retrieval stuff. Why don't we switch to it? Yeah, good. Hey, I can't point.
Oh, okay. You on 13 or 12?
12.
You're on 12, okay.
So people were addressed by their terminal number, 12 and 13 or something like that in this demo. You had to know, so I don't know exactly how you'd find out. They didn't have a directory yet.
Yeah, you had executive use.
There you go.
Where am I? There.
There you are.
Great. All right. Now, talking about hot retrieval. That's, you're going to have to defend that.
You gonna give it to me?
Yep.
Oh, okay. We've been talking about retrieval all afternoon, really. That's one of the main things you're involved in doing. Every time you're changing a view, you're doing retrieval, really. I've broken it up here into two main categories. The first where you have a known destination, the second where the destination is unknown. These really present two different problems, and there are different commands in the system, naturally, to take care of these two different things. Let's open this up, take a look at what we have under here. Oops.
Good.
Got both direct and indirect. In the first, where you're making an explicit specification, and the second with an implicit. Explain what I mean by this. In the first case, you're actually able to point at what you want at the information you're trying to retrieve and move it into view. With the jump to identity command, you're able to point at it either by the cursor or by using a pointer, as you've shown. Jump to name, jump to link. Again, you're explicitly specifying by giving the name or having the name occur in the text. For implicit specification.
All right, so here I think we're seeing the beginnings of information retrieval systems on computers. Now, no doubt, well, various countries, three-letter organizations or equivalents thereof had that kind of thing, but in a commercial thing on such a small computer as this, it was, it was the exploratory part of how do you get information out of the computer. The other thing I might want to say about the file storage is user accounts had the account and file directory structure was not hierarchical. I think you could have any user could have a total of 40 files, and that was an operating system limitation. So they somehow figured out how to make a lot of files accessible. But you might have remember hearing Doug talk about in somebody's file drawer in the office down the hall. So, all right. Let's see. Doug had what amounted to a product description, and that was just a few minutes. So I'm going to zoom in time to that, and that'll be pretty much the end. And then I have a few view graphs, a few things to say about, threads following on.
Describes this system that so-and-so offers. And that's going to be a very interesting challenge for us to utilize our tools for organizing and retrieving information. And the last thing here is just a little comment about, after all of this, what's the product that we're providing in this research?
Doug was just finishing off the comment about the Network Information Center. The Network Information Center, or the NIC, was the control spot for the ARPANET of the time. The ARPANET was a series of 56 kilobit per second lines going across country from node to node. And it was a fairly amazing system. The NIC could send a new software image to one of the ARPANET processors in the machine room in Boulder. We had what was called a TIP, a terminal interface processor. And anytime the NIC personnel wanted to, they could reboot the TIP, or they could send a new software version, et cetera, et cetera. And this line in the in his his PowerPoint basically talked about the ARPA interface.
Well, we're providing a sample augmentation system, the one we use. And not only that, it's an augmentation system that's provided to augment computer system development. And beyond that, we also are hoping that we're developing quite a few design principles for developing augmentation systems. And these, I hope, are transferable things. Let me I'd like to close and give you some description of the support we've gotten from the different people to produce this, and to acknowledge that. And back in Menlo Park, we've got quite a team of people surrounded by quite a bit of equipment that have been busy listening to us and trying to control and switch. And these monitors are up here where all the displays went. The cameras went for some use, and the displays go here so that they can monitor the different.
Okay, so this system was, they were using it, what's the right term? They were eating their own dog food. They were using it primarily to develop, and that was sort of the first non-Doug Engelbart speaker. They were using it for the documentation. They built it in a in almost a agile manner. They did not analyze it and then start the waterfall. They built something, I'm sure they abandoned some stuff, and but they built in an incremental manner. So I'm going to try to skip over to, I had some to say about the threads. The threads that came out from, well, sort of this work. It's not all directly from NLS. Okay, so what happened? What happened to all this work? Well, I don't think any of you probably have heard of NLS. So it's safe to say it kind of died. But there were a lot of hits of the things that they worked on. This interactive computing to augment human intellect. Other than numerical processing, basically the time-sharing computers and the batch computers were pretty much used for only the numerical stuff. The 940 had Snobol. If you tried to do string processing and basic, some of the basic programming language systems had strings, but they were hardly, more than, print out what do you want to do, and get the input. The mouse, well, that's a big winner. Function keys, well, I say function keys are what came out of the chord board. And then there are chords on the regular keyboard, Control Alt Delete being one of the famous ones. Document structuring, ergonomics at the very end that I didn't show, Doug acknowledges a furniture company that had a research division, and they're the people that built that keyboard, mouse, and cordboard combination. It was mounted on a chair and it would swing out of the way. So you could move it out of the way, stand up, you know, get out of your chair. I thought that was pretty nicely done. They looked a lot into how do people use this. Now, they were all used to memorizing 3-letter acronyms. That would not work today, but at least they started thinking about this. They had hypertext leading in their structured document that led to that, presumably in HTML. And they used the graphical user interfaces for at least some of the stuff, for selecting, not for giving the operations. Now I copied from Wikipedia. You can go to the NLS entry on Wikipedia, and there's quite a few firsts that they list. So we've talked about, well, hypertext, hypermedia, this outline and custom view. Not so sure about multiple windows, but at least the split screen seemed that. The email, I didn't show that, but basically what you did is you created a message and you said who it was from and who it was to, and you could select multiple destinations. You could search for email from somebody or to somebody. We saw the shared screen teleconferencing, formatting directives for memoranda or printout, for the printout for memoranda. The uniform command syntax, well, okay, but you know, that wouldn't work in today's very much in today's world. Now, there's some other things. Well, here's some misses. I think the cordboard is definitely the miss, just too hard to figure out. They didn't have menus, but I'm guessing that the user interface complications of having to memorize and memorize the 3-letter combinations and use the cordboard led to folks looking for something else. I also didn't show, they had search where you would actually edit a snippet of code to customize what that snippet would do. Then you compiled it, and if it compiled correctly, then you ran it, and then you could select for view the results of that custom search. NLS was the one and only in a couple of ways. One, that was the user app. You know, I don't think it was easy to add stuff to NLS. Although, again, NLS was just one command that you would run on your 940. So if you didn't want to use NLS, you could use the basic or the Snobol system on your 940, or you could run NLS. And the other one and only was that the document structure, that hierarchical document structure, was the only thing you could do. And if you couldn't fit your document, well, you had to fit your document into that structure. Another thing, as a successor, well, Xerox PARC. Eventually, the NLS project was not funded, and it kind of broke apart. Some of the Stanford Research Institute staff who were working on that went to work for Xerox PARC, and that's pretty well, the history of that and all is pretty well known. Another thing that peripherally came out of this, well, it's really out of the Project Genie work. Ken Thompson was a student at UC Berkeley, and he worked on Project Genie. I think his bachelor and master's degrees were in 1965 and 66, so a few years before this demo. The 940 system had what they called an executive that's similar to the shell. However, on the 940, the executive needed system privileges. The 940 had a null device, so dev null on Unix. I don't think systems before the 940 had null. I mentioned a couple of syspops to simulate terminal input and steal terminal output. So you could basically run, I forget the name of expect. You could run the equivalent of expect scripts and stuff input to a terminal and grab the output so that you could see if that was what was expected and then give the next thing. I know I used this kind of facility so that I didn't have to type the 20 or 30 commands that I'd need to type every 5 or 10 minutes when I reassembled or rebuilt some system. I think the Snobol had 5 or 6 files that had to be assembled independently, and then you had to do the link editing and save stuff, that kind of stuff. The 940 had a hierarchical process structure. I talked about DDT, the debugger, letting one map in the operating system. You could patch the running operating system if you were brave. You could also touch global or per user operating system data. I mentioned something like that when a user's terminal stopped responding, sometimes we could break it free. I did some patching, and I think my success rate was about 70% or so. And when I failed, so this was the days of teletypes, mechanical systems. And when you hit the enter key or the carriage return key, I forget what it was called, then the mechanism that did the printing moved to the left edge of the paper, and a separate character upspaced the paper, and then to allow for some mechanical bounce to die down, we usually had one more character that was just output for timing. It was like a Control A, which nobody cared about seeing on their terminal. If your patch didn't succeed, then what happened is you type the carriage return to say, enter the patch, or, enter the patch, commit it. And then the carriage would just drift to the left side of the paper, but it wouldn't upspace. And that's when you knew that you just crashed the whole 940. Something else at NOAA, where I worked in Boulder, after we read the Bell System Technical Journal paper about Unix, a university student, excuse me, he was also a classmate in Boulder High. He implemented email for all the 940 users in a month or two, assembly language software. So it took a bit more than it would take nowadays to do this, but we saw a whole lot of similarities or maybe extensions from our 940 operating system to what Ken Thompson and Dennis Ritchie implemented in Unix. Another thing that came out of Project Genie was the Berkeley Computer Company 500, the BCC 500. So some of the people who didn't go, sorry, some of the people at Berkeley, not at Stanford Research Institute, but at Berkeley, created the BCC 500. It was user program compatible with the SDS 940, but it had some dedicated processors for some of the operating system tasks. It was not a commercial success. And so eventually the hardware and the people went to University of Hawaii. Lloyd Fosdick, he was the CACM algorithm, sorry, CACM, Communications, the ACM journal. He was the algorithms editor and also department head at the University of Colorado. he passed on the opportunity to bring the BCC 500 to Boulder. We found that out a few years afterwards, and were very disappointed that we had never even gotten a call, since there was so much expertise relevant at NOAA in Boulder. I made some significant extensions to BASIC, sent a tape with the BASIC system to University of Hawaii. They gave me a login. I connected up to it through ARPANET, the terminal interface processor we had in our machine room, and the Aloha Net, that was the satellite-based data communication system in the mid-70s. And you know, I knew where the bugs were, so I could verify that that BASIC was indeed the BASIC that I had not gotten all the bugs out of. And then another thing we did was a co-ed project that stands for computing and editing, or communications and editing. We had ModComp computers. Those were 16-bit mini computers. The co-ed network handled terminal IO. It handled some batch capabilities, remote card reader line printer tapes that were connected through, I think at the time we had like about 4,000 bits per second modems from the Bell system. One of the users of this remote job entry system was the Great Lakes Environmental Research Lab. So that's local here to the Northeast. Co-ed handled swapping and user files, and we replaced the 32 megabyte monster with the 300 megabyte swappable kind of IBM-like disks. And I think that's about it. So thank you for your attention, and any questions. I'm gonna stop sharing. Couple of comments from the chat. As I said, you know, Doug was interested in things like Earhart seminar training, EST, and stuff going on at the Esalen Institute down in Big Sur area. And interesting about Ken Kesey. I didn't know that Ken Kesey had visited Stanford Research Institute. So let's see. I guess any questions, any comments?
Curious to know if it's possible those three-letter acronyms are the reason why stock names in companies are only 3 letters, because that's what they can fit into the computing systems.
Well, maybe, but my guess is that like the New York Stock Exchange probably hands out the 1 and the 2 and the 3 and the 4. I know AT&T is, its stock symbol is T, and my guess is that they got that by asking or paying. One of the attorney firms that just started here in Rochester, New York, has what's the phone number? 888-8 million or something like that. I'm sure they had to pay a pretty penny to get the 800-0000 phone number. Let's see. I think what I'm going to do is stop this. I'm going to go to share. I don't know if anyone is interested in this presentation, but I am going to, oh no. I was going to, oh, anyone with a link. Perfect. Copy link. And here's the presentation. I'll probably delete it in, well, not any sooner than a month from now, I'm sure. But so feel free. And let's see, I don't see any new questions. So I'll leave it to the RocDev organizers to close out the meeting. Thank you very much, everybody.
Awesome. Thank you. Let's get
Thank you,
started.
Howard.
Thank you.